1 second. Okay, good. Okay. Good morning. How are you? Fine. Thank you very much. It's important to start the week with some optimism, you know. So, and I don't know about you, but usually on Monday for me is the week, the day of the week where I am more tired because the weekend is very intensive, because the weekend must be intensive, okay? So the right life is to get tired during the weekend and rest during the week. Okay, just a note to start, a positive note to start, and I wanted to remind you that our timing on Monday is 9:15, 10:45, 11, 11:45. Usually I get into the room early, but I start at 9:15. And on Thursday, we will have a lecture online according to our calendar. Again, I will start lecturing at 9:15 up to 10:45 online, okay? And it means that there is no lecture in physical presence. It's only online on Thursday, okay? We have an amount of hours that is taught online only. And there is the calendar on the website right here. You see on the screen. Next Thursday is Feb 29, okay? And so I will start Teams a little bit early, even on Thursday, but I will start lecturing at 9:15. If you get connected and you don't see me, don't worry. You can start and access the room anyway. It's no problem. Just wait for me if you are earlier than me, okay? And I will give you some notes on how to best prepare for the online lecture on Thursday later today, okay? Good. Now, last time, according to the video, which is already online and available in YouTube and Virtuale, last time we worked on the first link, introduction. Let me just open it. And we got here, let me move forward. We made an introduction to climate change. It was very basic. Oops. I think we got here, okay? And now let's move forward with this introduction to climate change. It is very basic, and then we will have a second introduction later on, but it is more detailed, okay? What I said last time is pay attention to these numbers because they are kind of orders of magnitude, and you may find some questions in the quiz or in the oral related to these numbers. Of course, I'm asking the order of magnitude, not really the right number. So, for instance, global CO2 emissions per capita increased from 2 tons in 1940 to about 4.5. If you say 4 instead of 4.5, it is fine. If you say 45, it's not fine. So it's just the order of magnitude that you have to learn, and I explained you why, because otherwise it means that you don't know the magnitude of the process of climate change, okay? So pay attention to these numbers. I will give you later on a trial exam, but later on, okay? Because of course, if I give you the trial now without the lectures first, you cannot take advantage from it. Okay, now some details now about the impacts of climate change. The impacts are what concerns us, of course. It is the risk that is induced by climate change. We will dedicate a lot of time to understand risk induced by climate signals and climate change in particular, in order to make a quantitative assessment of the risk. Quantitative assessment because we are supposed to devise actions, strategies to adapt. So we need this quantitative assessment, but first of all, we need to understand what we are talking about. Climate change, you know this because the media are emphasizing the negative impacts, the concerns related to climate change. We can split the impact according to the climate signal that we are talking about, the climate variable. Temperature is one climate variable. There are other variables that are relevant to climate, like, for instance, rainfall, wind, or humidity, etc. Let's talk about the main impacts related to the associated variables. So global warming is a matter of concern, and it's related to temperature, okay? So here there is a quote from National Geographic: Earth is warming up and humans are at least partially to blame. This is again from National Geographic. The causes, effects, and complexity of global warming are important to understand so that we can fight for the health of our planet, okay? I think it is important. National Geographic is supposed to be, it's a well-known source of information. It's important to emphasize what they say about the human impact, the human causes. The humans are at least partially to blame, at least, okay? So it doesn't exclude that the humans are completely to blame. It doesn't exclude that there might be a component of climate change which is natural, and this is what we need to understand. So global warming impacts the environment, and what is important here, it's also the subtle impact that we need to understand. There is a direct impact, a striking impact, which is related to the fact that we are more exposed to hot waves, that the weather is warmer. But there are also some indirect impacts, like the change in seasonality. Change in seasonality is something that, maybe not so striking as an impact. Actually, it has relevant implications, for instance, in water resources management. We will see examples. It's important to take into account that global warming is not uniform. I already mentioned this to you. There are hotspots. For instance, I think I already mentioned to you that the Alps are warming up with a faster rate with respect to the global rate, and we don't understand why. There might be several causes, but we don't understand why. Agricultural practices are impacted by global warming. Agricultural practices are much relevant for food production, and indeed the food production and the nexus between water, energy, and food, the so-called water, food, energy nexus, is impacted by global warming, and it's extremely important because, of course, water has an implication with energy production and an implication with food production. Keep in mind that of the global water consumption, about 70% is used for irrigation. So if there is an impact on precipitation, there is an impact on water resources, there is an impact on food production. The impact on food production is relevant, especially for the countries that have a lower gross domestic product. So it is indeed an impact that is important. Other impacts, weather extremes, like, for instance, floods and droughts. Climate models show that weather extremes may be exacerbated by global warming. Climate models show that. If we look at data, it's not so clear. Okay, it's not so clear because the weather extremes are difficult to measure. We don't have long records, and the records that we have, the few records that we have, actually they don't clearly indicate a widespread increase of weather extremes. On the other hand, we observe more and more frequent floods. So it's clear that this is anyway a global concern, irrespective of the causes. It's something that we need to adapt to. Risk of flooding. It is, we suppose, anyway, climate models say this, but we think it is reasonable that precipitation extremes are increased under global warming, especially for short duration rainfall. This is what we suspect. For short duration rainfall of the order of length of 5 minutes, because, you know, we classify rainfall depending on the duration of the event. We may have short rainfall, long rainfall. We know this from our experience. There are some rainy perturbations that last for 1 week, and there are storms that last for a few minutes only, but they are anyway dangerous. The long precipitation extreme, the short precipitation extreme, they are anyway dangerous. And try to understand what kind of danger, what kind of hazard they originate, because the flooding originated by a short rainfall is much different from a flooding originated by a long rainfall. If you think of a rainfall that lasts for 1 week, and you think to the associated flooding, like Po River floods, Tevere River floods, Arno River floods, they are different with respect to the floods that are caused by 5 minutes of rain, which are typical of small creeks, small torrents. They are nevertheless dangerous, but they are different. Try to associate in your mind, in your expectation, what are these differences? We will talk about these later on, but in your mind, try to elaborate an expectation, an intuition, because this helps a lot to remember what you study, helps a lot to understand better, okay? And it's not clear if climate change is affecting the memory of these processes. I try to be clearer. We observe sometimes cluster of floods in time. So when we get a flood-rich period, it's so-called flood-rich period, we observe that this period tends to persist. The same for droughts. Sometimes we get drought periods and they persist. And we don't understand why there are these cycles. It's not clear if climate change is affecting these cycles. I want to give you an example. We have in Bologna a long daily rainfall series starting from 1813, continuous daily rainfall, continuous measurement from 1813. So it's already 212 years. So this is a unique opportunity. It's one of the longest rainfall series available to humans. It's a unique opportunity to study the climate of the past. And from this series, we observed that in the past, we had several droughts that lasted for several years, like 5 years, 8 years drought period. When I say drought, I mean that for 5 years, 8 years, we get 20% less precipitation. So it's much. It's really much. The last one of these events was in 1945. And then we had droughts, but not so long droughts. We had a drought in 2003 in the full north of Italy, but not so long. It lasted for 1 year. We had a drought in 2022, but it lasted 1 year. In 2023, unfortunately, we got floods. I'm talking about this region, but when we talk about droughts, usually they are much extended in space, okay? So what is the reason why in the past we got several long-term droughts up to 1945, and now we are not getting any? In the past 70 years, it may be just a matter of chance, because climate is governed also by chance. So it may be that next year we start with another long-term drought. It may be that climate change is decreasing this kind of risk. It may be, because we really don't know. Climate models don't reproduce these phenomena. Climate models up to 2100, they don't predict for this region, several different models we consulted, the repetition of a similar drought event. So given that these clusters of events, these long-term events, mean that the process has a memory, the process remembers its state for a long time. So when I get a shock, a drought, it is remembered for a long time. It's not clear whether climate models can reproduce this memory. Just to give you an idea of the uncertainties that are inherent in this subject. Okay, so another risk. Floods and droughts are related to, I already talked about them actually. And so I think there is nothing that we can add here. This is a picture from the US Drought Monitor. There are several websites providing you environmental information. We will explore some of them. Okay, I just want you to know from the beginning that if you are interested in climate change, in climate in general, there are a lot of public websites making data available, a lot. Okay, floods and droughts are indeed, I want to stress once again, an important impact of the climate signal. Keep in mind that the impact of climate is mainly through the water cycle, as we said last week. And so it's extremely important to keep this into account. Correct interpretation of the water cycle, it's essential to decipher the impact of climate. What we need to do, because if we want to adapt, adaptation means mitigation of the impact. So we have to understand the impact in a quantitative way. Hurricanes. Okay, two quotes. I think it's important to read them. From NASA, from NASA, climate models predict hurricanes will likely cause more intense rainfall and have an increased coastal flood risk due to higher storm surge caused by rising seas. Additionally, the global frequency of storms may decrease or remain unchanged, but hurricanes that form are more likely to become intense. So NASA, which is a very reliable source, says that hurricanes may increase, the risk connected to hurricanes may increase in the future. IPCC, another very reliable source. I will explain in a subsequent slide what IPCC is. Globally, there is low confidence in attribution of change in tropical cyclone activity to human influence. This is due to insufficient observational evidence, lack of physical understanding of the links between anthropogenic drivers of climate and tropical cyclone activity, and the low level of agreement between studies as to the relative importance of natural variability and man-made forcing. So you see two slightly different interpretations. And NASA says that it's very likely that climate change is increasing this risk. IPCC says that we can't say that. We don't know. It is not excluding, but they say we don't know. Again, look at the uncertainties and the need to improve our understanding. Sea level rise, this is another important impact. So from NOAA, another is the National Ocean and Atmospheric Administration of the United States, another very reliable source of information. Global average sea level has risen about from 24 centimeters since 1880. Keep in mind this increase is at a more or less constant rate. So it's not like global warming, which increased with an higher rate in the past 30 years. Sea level rise started to increase since 1880 with a quite constant rate. After 1990, the rate is very slightly increased, very slightly. So the rate of global sea level rise is accelerating, as you can see here, as I mentioned. It has more than doubled through the 20th century. And but when we will see the graphs, you will see that it's not an increase like global warming. It's smoother. And sea level rise is not constant everywhere. The sea level is not constant everywhere. The sea topography is not such to set a unique sea level. there are changes due to tides, due to wind forces. So even sea level rise is not constant. It has an important impact, not just because there is evidence that we may lose a lot of land soon. This is not the major concern. Usually the media emphasize this concern as with a high priority. So losing lands for sea level rise, actually with this rate of increase, there is no evidence that we are going to lose a lot of land. But we are not sure what's going to happen with storms, coastal storms. And another important effect is salination, because even a small change in sea level implies a big change in saltwater intrusion into the land, which is a very relevant impact because it causes salination of fresh water. And we are not focusing on it now, but it can be easily proved that even a small increase in sea level causes a huge increase in saltwater intrusion in the underground, into the land, and into rivers. And this is particularly concerning, as I said, for freshwater availability and for the implication in coastal ecosystems. Now, let's dedicate a slide to the positive impact of climate change. Just 1 second. Sorry. Positive impact of climate change. There are positive impacts, of course, as we know, because we know that in the past, the Earth system underwent big changes in climate, and these changes in climate had a positive impact. Warming has a positive impact because we may have possible less mortality for cold waves. Okay, you may have more mortality for hot waves, but if we focus on the positive impacts, we discussed earlier the negative impacts. If we discuss on the positive impacts, of course, with warmer weather, at least in some countries, we feel more comfortable. By the way, there were studies proving that the periods of prosperity in the human history were the period of warm climate. Because it has been observed, according to the records, that usually the cold weather is associated to more flooding. And only the recent times makes an exception, because in the recent time, in the past 30 years, we had indeed an increase of flooding in a warm period. But if we look at the historical period, with cold weather, there is a decrease of food production. So there is an impact on the welfare. And there is an impact also in terms of natural hazards, because it has been proved that the biggest floods documented in the history occurred during cold period. Okay, we may have decreased avalanche risk, and this is not much relevant unless you are a mountaineer. And farmers in some region may benefit from the earlier onset of spring and from a longer growth season. And also crops may benefit from the increased CO2 concentration, because CO2 is a fertilizer. And the tourism may benefit from a warmer climate. Shipping commerce may benefit because the opening of the Northwest Passage may allow an easier communication along the pathways in the oceans. And the North regions may benefit from an expansion of agriculture. And indeed, changes in climate in the past occurred, and the humanity was able to adapt. The big question is that, now we have a society that is organized in a different way. It's the societal system has a higher complexity. So adaptation may be more complicated than in the antiquity. And there is also to say that now we are less keen to, in a way, to accept an high cost for adaptation in terms of human death, or in terms of implications on the human health. We are not so keen. I mean, in the past, the value that probably humans attributed to their life and their health was lower than today. Now, the complexity is increased. And in any case, a direct implication of climate change is migration. When you have a climate change, it means that some part of the Earth become more favorable to living conditions, and other parts become less favorable. So people tend to migrate. Now, currently, migration is motivated by also other drivers. But indeed, there is a part of the current migration that is also triggered by climate change. I would say that it's still not a significant part. If we said that today climate change is responsible for migration, we wouldn't be realistic. There are, what are the causes? And political causes are dominating today. But still, migration, when it happens, it causes wars. It causes tension, international tensions. So, I mean, this is the constant. We have to find a way to adapt in a way that avoids these societal implications. Okay. Now, what is the IPCC, the Intergovernmental Panel on Climate Change? The IPCC is an international institution that has been created by several international countries in order to study the effect of climate change. And IPCC is working intensively starting from, I think it was established in the early 2000s. The first report that they published was published in, I think, in 2003. And they already published the so-called assessment reports, 6 assessment reports. The last one is going to be published now. Some part of it have already been published, the 6th assessment report, and other parts, other chapters are still to be published. Let's click on this link, which I think is a Wikipedia link. Let me see. Here it is. And let's look at about. So it is a panel of the United Nations for assessing the science related to climate change. And the IPCC provides regular assessment of the scientific basis of climate change, its impacts, and future risks and options for adaptation and mitigation. It's a panel that is made by scientists. They are selected among several disciplines with probably there is a larger number, there is very high proportion of climate scientists, but there are also hydrologists and atmospheric scientists, etc. Let's see about the reports, which is what is interesting for you. Okay, let me see. So you see here the 6th assessment report. The 5th was published in 2014. And the 6th was published in 2023. But as I said, you see that some chapters were published in 2021, 2022, and some of them are still to be published. If you click here, and here there is the link. And if we go here, there are several documents. These reports are not easy to read. Why I am dedicating some time to it? Because if you're interested in the subject, this is indeed a source of information that is very interesting. I would say that it's a scientific information, but not. It doesn't provide guidelines for designing strategies. It doesn't give technical indication. It doesn't give socioeconomic indications. But still, I mean, for knowing the scientific basis is extremely important. And there are some summaries which are easier to read. So read the report. 1 second. You have to follow several links. Summary for policymaker. This is a summary that is easier to read. And there is the longer report, and the longer report is divided in chapters. So there is a chapter on the water cycle, on the hydrology, on floods and droughts, etc. Now, the IPCC, as I said, is a relevant source of information. You have to keep into account that the topic of climate change, as I already mentioned to you, gives rise to some controversy, even in the scientific community, not only in the socioeconomic community, but also the scientific community is discussing a lot on several different questions. There is not a unique question that is discussed. There are several questions which are still debated. And one, the most controversial, is probably the attribution of climate change to humans rather than natural variability. But there are many other questions, like, for instance, the hydrological impact, the impact on hurricanes. And you see that these questions are still debated. So indeed, even if the IPCC is an institution of the United Nations, it's a panel of the United Nations, it's not the unique source of information. And if you want to get very, large view of the big picture, a very comprehensive view of the big picture, you don't have to limit your source of information to one source only. This is a general rule. Okay, when you want to get the big picture of a topic, you don't have to rely on a single book, especially if the topic is subjected to some uncertainty, some controversy, some debate. Then you have to refer to several sources of information. Okay, so don't limit yourself. If you want to become a climate specialist, an engineer maybe who is very expert on climate, you don't have to limit your view to IPCC, and you don't have to limit your view to any other single source of information. Keep this into account, because you are an engineer, so you bring, not all of you, but most of you are engineers, and you bring the responsibility of of the projects that you sign, where you put your signature on. Okay, but I think this information is extremely relevant. Okay, now 1 second, I go back to full screen. So what does IPCC say? It says what we already discussed. Models can simulate recent warming only if anthropogenic forces is included. And the current rate of warming is unprecedented in the past 2,000 years. If you go back furthermore in the past, you can find other periods with an higher rate of warming. And pay attention to the terminology, the current rate of warming, which doesn't mean it's the period with the higher temperature. Because in the medieval warmer period, and you can see it more or less around here in the graph, if you look at, here, if you look in my mouse, there was a period that was it was warm. And then you see that there was a decrease, and then another increase, and then a sharp increase in the past few years. But there are still some doubts, because these are observed data and these are proxy data. Proxy data tend to smooth out variability. So proxy data don't tell us if there was a peak in the medieval warm period. So here you see that it was warmer, but like constant. Actually, there might have been peaks. Basically, basing on reports, oral reports, we know that glaciers in the Alps were less extended than today during the medieval warm period, because we know, for instance, that people crossed the Teodulo Pass between Italy and Switzerland just by feet. Now it's not possible. You have to wear crampons and you have to to take a rope and whatever. You need equipment for mountaineering. And in the past, we know this, that people crossed it. And we have also, in the Dolomites, we know that the woods were extended to up to a higher altitude than today. So, you know, it's something that needs to be explored, but it seems that the rate of warming is unprecedented in the past 2,000 years. It seems so. And now, here you see a graph. So model simulation from 1850 to today. And if you simulate with model with only the natural component, you get a kind of steady situation. If you get if you feed into the model the increased CO2 emissions, then you get an increase of temperature. So indeed, models confirm this. Okay, now this slide says what I already anticipated. Water-related disasters are the most impactful climate-related event. So here you see the costs of the climate-related disasters. So hurricanes, okay, it is water-related. Droughts, floods, again, droughts, floods, flood, storm, drought, floods, everything is water-related, as you see. So here there is a questionnaire. In your opinion, is the frequency of floods increased at the global level? So we may say no, we may say yes for land use change. Yes, it's not clear what the drivers are and what is their relative contribution to frequency raising. And yes, it is increased after climate change. I think this questionnaire, it's interesting to emphasize what other drivers may have caused an increase of floods. Climate change is one of them. Land use change, there are several researches focusing on the impact of land use change on frequency of flooding. Land use change implies not only deforestation, not only urbanization, it also implies the modification of the riverbed. It is a very local land use change, and it is proved, we know that. If you restrict the riverbed, you of course increase the risk of flooding. It's clear. I would say it's trivial. And the river tunneling is another problem, which is relevant, especially in Italy. We tend to tunnel the rivers, to cover the rivers, because we want to gain room. In Italy, we don't have room enough. Italy is a mountainous country. We don't have enough space. So we tend, in the big cities especially, we tend to cover the rivers in order to put houses over there or streets. But river tunneling is a dominant cause of flooding. And it is difficult to solve it because once you tunnel the river and you build an infrastructure over it or houses, the only way to untunnel the river is to remove the infrastructure, remove the houses, and you understand it's not easy. And give back to rivers their room, it's not easy because you have to keep a part of the land which is favorable for human settlements, reserved to the river, give it back to the river. It means that you have to remove houses, you have to delocate people, you have to move people. It's not easy. So here the right answer is yes, it is increased, but it's still not clear what the drivers are. So for sure, flood frequency is increasing, and it's increasing for a combined effect of different anthropogenic impacts. Climate change and land use change are the most important drivers, and their relevant contribution, this is extremely important to emphasize, varies depending on the local conditions. River tunneling is a local condition. So their relative contribution, the relative contribution of climate change, the relative contribution of land use change, it's really local. And we need a local analysis, a local assessment. We cannot use global models because global models have typically, they are coarse, they use a coarse resolution. They cannot describe river tunneling. A global model cannot describe a river tunnel, cannot incorporate this information. So we cannot really estimate flood risk with global models. This is a bit of a problem because there is a part of the scientific community that claims that we can estimate flood risk at the global level. Actually, we have to emphasize that really it's not the case. We need a local assessment. Furthermore, keep into account one thing. Usually disasters are caused by the unlucky combination of causes. Usually when a disaster is really a disaster, it's the combination of more than one cause, more than one driver. And the same when we make mistakes, there is a say which says, okay, did you make a mistake? Fine, be careful not to make the second one. Because usually the highest implications in our life, the highest, troubles, are caused by a combination of mistakes, which is not unlikely. It's not unlikely because when you make a mistake, you get in an emergency situation. And then, of course, the risk of a second mistake is larger. Like when you make a car accident, okay, you crash. The first thing that you have to say to yourself is, okay, I crashed. Let's not make the second mistake. The second mistake may be that you get out from your car and you get invested by another car running on the street. And the same for climate and floods. These different causes are related. Land use change alone, if you don't get an extreme rainfall, it's not a problem. And if you get an extreme rainfall without land use change, it's not a problem. Or maybe not a problem. But you get an extreme rainfall, and then over land that was changed with the river tunneled, and then it's a combination, and they are related. So it is important that we study also this combination of causes, the co-occurrence of causes. And studying their implications, it's not easy. Okay, so far we learned that there is uncertainty in the topic. It shouldn't be a problem. We are used to deal with uncertainty every day in our life, especially if you are a scientist. You are used to deal with uncertainty. Uncertainty can be dealt with in several different ways. You can make a very rational analysis. A very typical engineers, what they do when they have to take a decision in the presence of uncertainty, they evaluate the risk in taking one decision, they evaluate the benefit, and they make a cost-benefit analysis, and they decide. Other people decide based on what they like. Like if I have to take two different roads to get to my final destination, the engineers calculates the distance and then the traffic on the left way, and then distance traffic on the right way, and then decides. And there are people who make a decision like, I like to go on the right, and I go on the right, irrespective of the time that it takes, the cost, etc. So there are several different ways to deal with uncertainty. If you make a design project, you are required to very often to follow guidelines. So just make sure that you deal with uncertainty in the way the guidelines or the legal requirements suggest. So uncertainty is not really a problem. It's something that we can deal with. But of course, we have to realize that uncertainty also applies to climate, to meteorologic prediction, to climatic predictions. There is no certainty in natural processes. I say this because in this period, in this, let's say in our era, the increase in scientific knowledge, in scientific methods, tends to give, and the media tend to give, the feeling that we can predict climate with certainty, or the meteorology with certainty. This is misleading, and I would say it's extremely dangerous. I give to you an example. For instance, when when the flood in Tuscany occurred, I think it was September or October, I don't remember the month, in 2023, the civil protection was blamed because they raised an orange warning. The civil protection issues warnings, which you can find on their website. And you may know also that in Italy now they are launching a new service with short messages on mobile phones. They issue warnings, and the warnings have different colors. So there is the yellow warning, the orange warning, and the red warning, of course, increasing expected risk. An orange warning, it's something that it's already relevant. I mean, if you get an orange warning, you should get concerned. The civil protection was blamed because with a flood, people was expecting a red warning, which means that the message was not understood. Because an orange warning, it's still relevant. You cannot exclude to be flooded because there is uncertainty. And also, if you read the guidelines of the civil protection, they clearly say that with the orange warning, you don't have to stay, to feel relaxed. It's a warning. But people didn't understand that. And they were taken by surprise by the flood. This is a relevant problem today, that we are still getting flooded by surprise. We don't expect to be flooded. Actually, if you look at the map of Italy flood risk, almost all of Italy is at the risk of flood. So if you live in Italy, almost for sure your home is in a position that is exposed to floods. But we don't expect them. We kind of say, why should a flood occur? In my memory, in the memory of my father, my grandfather, my grandmother, my mother, they were never flooded. So it's a clear demonstration. But actually, climate has a time scale that goes beyond the human memory. And so we don't remember what our grandparents experienced. We don't know that. And so, it's important to be aware of the risk and the uncertainties. What is the reason of uncertainty? This is another question. So, imprecise information, limited predictability, which means that it's not necessarily due to lack of knowledge, or maybe lack of knowledge, and therefore it can be eliminated. And what is the correct answer? I tell you that it's not an easy question. The scientific community is debating. Will we be able in 1,000 years from now to precisely predict the evolution of weather and climate? Or it will be impossible forever? Okay, at the present, we know that uncertainty is certainly part of it given to lack of knowledge. Knowledge means not only lack of understanding, means also lack of data. But we also know the theory of chaos, which says that some natural processes are unpredictable and will be unpredictable forever. So what I would what I would choose here, of course, I am biased because I did it, but I would choose this one. So means limited predictability. This is important to know for us. Uncertainty is limited predictability. And even if the knowledge of the process is perfect, but this is my personal convincement, I tell you, there are people, some of my colleagues, instead think that we can get to the stage where predictability will be perfect. Predictions will be perfect. Anyway, I want to give you an example. Think of tossing a coin. We have a perfect knowledge of the process. Perfect. But we can't predict it. And we will never be able to predict the outcome from tossing a coin. Never. And I don't see the reason why natural processes should be different. Okay. What is science then? We talked about uncertainty. Let's talk about science, because science indeed allows us to reduce uncertainty. It's our task to take the approach that minimizes uncertainty. Uncertainty is not negative, but we have to minimize it. Okay, we can deal with uncertainty, but we have to minimize it. So science, I think it's important to look at the definition, is a systematic endeavor that builds and organizes knowledge in the form of testable explanation and predictions about the universe. Testable. We have to look for something that if we use a method, if we use an approach, we have to test it. Or if it's not possible, we have to make sure that it's not possible to use an alternative approach that can be tested. Testing is important. You cannot blindly rely on a model without testing it. Okay, somebody may have tested it for you, that's fine. But testing is important. The interpretation of testing and validation is, of course, subjective. Of course. People try to test models by comparing with alternative models. Other people compare with data. The people who test the models with other models, they say that they trust models more than data. We already discussed about this. Just make sure to, especially if we put your signature under a design project, make sure that you make an objective assessment of what you do. And in fact, the history of science is studied with erroneous conclusion. There are a lot of erroneous conclusions. I'm not making examples, but you know that, for instance, okay, one example I make, Galileo. Galileo, the Pope apologized, I think it was like a few years ago with Galileo. The church apologized with Galileo after 500 years. And Galileo was, of course, was correct. And but he was not believed, and it was even condemned for his theories. Aristotle, and so there are several examples. Okay, so what is the discipline that is most related to climate? After what I said, hydrology, of course, but I am biased again because I am an hydrologist. Okay, I am almost there. Last slide, just to introduce now our next discussion. How can we devise climate actions? Okay, in order to understand how climate change can be mitigated, in order to understand how we can adapt to it, we need to understand the climate change through science. This is our first step. And then if we use models, we have to test them. So what are the basic questions? What is the magnitude of climate change? And we already saw some orders of magnitude, but I also said that for extreme rainfall, it's not clear the effect of climate change, to what extent climate change is affecting it, how climate change is affecting water, socioeconomics, and public health, because it's not fully clear. And the implication, the implication on the water cycle, if climate change is not clear, it's not fully clear, the implications are even less clear, because you need a cascade of interpretation. What are the causes of climate change? How we can generate future climate scenarios? How can we estimate the future climate? As an engineer, if you are an engineer, you are required to do that. You have to make a design project against climate change, to adapt to climate change. You have to make a prediction of how the future climate will be. So should we use climate models? What are the solutions? And uncertainty, okay? Here, a self-serving reading, because this is a paper that was published on the Po River the last year, which shows that climate change caused the change in seasonality. And it's a problem in water resources. I think I already mentioned this effect to you. Global warming means anticipated snowmelt, means less snow. So it means less storage in the Po River basin, where 60% of the Italian gross domestic product is produced. So if you get less water in summer because there is less storage, it's a big problem. Indeed, if you look at the biggest droughts in climate change for the month of July, you see in the first 10 droughts, six occurred after 2000. So, I mean, it's not clear the effect of climate change on meteorological droughts, rainfall, but in the river flow here, for the Po River, it's clear. Global warming, it's clear, the effect. Okay, fine. I think we can close this. Questions? No questions. The second link, just read it. It's not for the exam. It just says, I mean, few words on it. It just says, what is the purpose of this course? The purpose is not only to study climate change, study adaptation, but I also would like that you know these are the 21st century skills. There is a Wikipedia page. So during your learning, try to focus on what are the skills that are believed to be important today. You may not agree with some of them, but it doesn't matter. I mean, these are the results of discussions among several educators, professors, and academicians. I think it's interesting because indeed, I think the way you should study today is different from the way students studied 20 years ago. It's different. And now we have to be more creative, more acquainted with the digital literacy, more expert on the PC. And if I look back 10 years ago, it was impossible to see students with the notebook open, also in meetings. Now everybody in meetings, administrative meetings, has a notebook. 10 years ago, students used to take the audios with the mobile phones of the lectures. Now nobody records the audio of the lectures. It's completely different story in 10 years. And not only for the pandemics, absolutely. Okay, of course, the pandemics caused an acceleration, but it is a big change that is undergoing. And I think the change really, the rate of change is really higher than in the past in terms of education. In the past, we used to use books for academic teaching for like 50 years. Now it's absolutely impossible. If you use a source of information after 5 years, it's outdated, completely outdated. So it is indeed interesting to read these skills, and for you it may be useful, but this is not related to our subject. So it's not related to the exam. So just focus on them by yourself. And it's a link that I wanted to provide because I think it is interesting. Okay. Questions? Okay, before I move forward, I want to, given that you don't have questions, and in order to relax a little bit, I want to show you a data repository, which is interesting. And so it is linked somewhere, probably already in the introduction. Let me open another window, and I hope that I can find it. So let's look for the climate data store. Climate data store, and okay, 1 second. Copernicus climate data store is the first link. Let's look here. This is a website with open information about climate, not only climate change, climate. There are a lot of numbers here, which, I mean, if you're interested in the topic, it's a good opportunity. maybe for your thesis, for whatever. And the problem of these repositories is that you need some digital literacy to interact with them. So let me just make an example, and let's go to datasets. Here you see a lot of them, or like climate suitability indicators for tourism for 1970 to 2100 over Europe, derived from climate projections. Interesting. And here you see, let me see if I can open you can see with different colors, okay? Suitability for tourism. Okay, good. And several other links are available here. Near surface meteorological variables from 1979 to 2019 derived from bias corrected reanalysis. What does it mean, reanalysis? Means that these are data that are interpolated over space in order to get a global coverage. So for instance, here you see, let's see, monthly mean near surface air temperature, January 2018. And of course, you can make this map, you can make an animated map which shows to you the progress, okay? And okay, several others. Now let's go to, the problem is that, I forgot to say this. If you want to download the data, these are gridded data. Gridded means that they are global data, which are given over a grid that covers the whole globe. A grid means a cluster of squared cells that cover all the globe, which means that you get a lot of data because the resolution is quite detailed, maybe like 25 per 25 kilometers of the cell. So to cover the whole globe, you understand, it's you get a lot of numbers. And to manage these numbers, it's not easy. And typically they cannot manage in Excel. You need a geographic information system. So I think you took some basics on GIS, geographic information systems. But still, you know, you need this literacy. And now let's see toolbox. This is particularly interesting because with this toolbox, you can, let me make a login, because you need to register, which is not a big problem because they don't send you anything by email. I hope I remember the password, because last time I logged in was, and okay, perfect. And what you see here, it's a window where you can extract the data, but you have to work in it in Python. Python is a programming language. And if you know Python, is very easy, because also here there are examples of codes. For instance, I'm not an expert of Python, so what I did is for taking this rainfall in Bologna, for making this rainfall in Bologna request, what I did, I got an example from this list and I put the coordinates of Bologna. And what I got is this code. If I run it, let's see how long it takes. It should display a graph of rainfall in Bologna, annual rainfall here from, you see, up to 2100. And this is, let's expand it a little bit. Okay, 1 second, because it is, I can't reduce, let me see. Okay, anyway, it's monthly rainfall from, I don't remember the start, let me see, I think it is from 1950 up to 2100. And what you can see here is precipitation, and the unit is a bit strange, but it is, if you want to look the pattern, it's precipitation. Is the unit doesn't matter if you want to just look at the pattern. And what you can see here is that this is taken from one single model. There is no clear trend, okay, in terms of monthly precipitation. The problem is that in order to get this data, you need, as I said, some literacy, because this is not a long code, but still you need to know Python, and then you need to write your instructions. Here I put the coordinates of Bologna, you see here, longitude and latitude. So you can change these, 46, and then you run, and then you get a different graph. I can't expand the graph. Okay, anyway. And it takes some time because for Bologna, it was already extracted. And here it needs to extract the graph. Anyway, that's it. Another indication that I want to give you, it's another source of information is CMCC, and it's climate change maps. Climate change maps over Italy. Climate scenarios from Italy. This is given by the CMCC. It's a national. It's the Euro-Mediterranean Center for Climate Change. In Italian, it is spelled Centro Euro-Mediterraneo Cambiamenti Climatici, CMCC. And you can get here a useful information, which I sometimes suggest to, in the form of maps. I suggest to users who want to get a quick overview of the impact of climate change in Italy. So this is, just one second, it's, let me check how to get the maps. And okay. Presenting these maps, okay. 1 second, maps, okay, here it's Italian or English. No, it's only Italian, sorry. Maps and indicators. So here you can select the scenario. We didn't talk about the scenarios, but these are scenarios of future CO2 emissions, okay? So the higher the number, the first digit, and the higher the predicted future emissions. Let's take 8.5, which is the worst scenario. The period, let's take 2021 to 2050, and the variable is, let's say, temperature. And here we should get the map. Still not there. Okay. Model. Okay, let me see. It's only, okay, good. Here is the map. And this is it should be the climate anomaly, and up to 2100, and you see +1, +1.5. Another interesting information is extreme rainfall. 95th percentile means extreme rainfall. And here you can see the same scenario, and you can see the percentage increase in rainfall up to 2100. If you look at this map, in a way, it's a bit, it's not very homogeneous. There is a lot of variability, which gives to you an idea of the uncertainty. And here, it's only one model with a resolution of 8 kilometers. It means that the cells have a size of 8 kilometers. But as I said, for instance, I was asked by a water board, what is the increase in extreme precipitation that I may expect in Bologna for up to 2100? And I said, okay, look at these maps. It's the easiest way to get this information. And they didn't want to spend much time on it. So I think indeed CMCC, in preparing this map, did a very good service, and you have to be aware of the uncertainties. It's only one model, and if you look at the map, you get an idea that there is uncertainty because it's not clear why. For instance, if you look in the Padana plane, the reasons for this variability in increase in precipitation, which is not negligible, because if you look at the colors, it goes from there are some spots with plus 30% and some points with 0. They are very close together, so it means uncertainty. So, for instance, if I look at this map on the Padana plane, I would say no change everywhere, because I wouldn't say, okay, in Bologna there is a change, but in Modena no, Reggio Emilia no. Difficult to justify. Okay, so I would say no change everywhere. While in Sardinia, I would say on the east coast, there is a large increase of extreme rainfall. In the west coast, there is still an increase, but not so large. Don't ask me the reason, because there might be several different reasons. I'm not involved in this modeling. And in order to understand the reason, you should look at the results, but not only the results, the state variables of the model. What are the state variables? All the variables that the model uses to compute extreme rainfall. So maybe wind velocity, maybe air pressure. So wind velocity may be different from one coast to another coast. So you have to look also at the state variables. And, it's not easy. It's something that requires some study. Keep in mind that when we are asked to make an assessment of the impact of climate change on flooding in Bologna, last time I asked for 1 year of work to complete the study, because it means that one has to download the data, study the models, because you can't use a model result without knowing how the model works. You have to study the model. Okay, let me see what is the resolution, what are the equations, look at the model has been tested or not, and what kind of testing against other models or with the data. And there is a lot of work. And also study the historical data that we have in Bologna. So is the model matching with the historical data or not? It takes a lot of study. So as I said, last time I asked 1 year of time in order to complete a simple assessment, because it becomes a bit complicated. Fascinating, because it's very nice if you like this kind of approach and this kind of problems, give a contribution to solve these problems. And if you like the fact that it's not an easy problem, which means that when you are able to solve it, not everybody is able to. So it is also stimulating because you give a contribution that is unique, which means that you can really contribute. And our dream is to make a contribution. Anyway, just to relax a little bit. There are a lot of sites giving data. The problem is that we have too many. And it is a recognized problem. Now we have monitoring systems that produce an amount of information that is massive. It is a recognized problem that we are producing information, but we are not able to use it for several reasons. This is a recognized scientific problem. And there are some international institutions that gives prizes in money to people who can devise ways to use their data. Copernicus is one of them. They give money to people who can prove that the data are useful, how to use their data. They give money. Okay, what time is it? Let me just introduce the next lecture. So, in order to understand climate, we have to understand how the Earth system works. So this is a lecture that is in the form of a web page, and let's take the PowerPoint because otherwise it's too boring. What is the Earth system? Okay. Stupid question. But in order not to give a wrong answer, let's look on the web. Earth system. Look, when I was a student, it was only 30 years ago, this was impossible. I had to go to the library, ask for the book, fill a form because they wouldn't give me the book without the form. I couldn't bring the book out of the library. I couldn't make any photocopy. So I had to take notes and copy the book on my notes. And now, Earth System, here we are. And I prefer to go on Wikipedia. And in English. Okay, it only talks about the science of the Earth system. And I don't like it. So let me just go back to Earth system definition. Otherwise, I give to you the definition, but I prefer. Okay. First, let's look to NASA. It's a reliable information. When you make a search like I did now, and you click over a link, make sure that the information is reliable. And this is the ability, the digital literacy that you need. So you need to gain skills to browse the web for the very reason that I just mentioned, that now it's our main source of information. The problem of the web is that you put a keyword and you get like 1 million entries, and you have to be able to recognize what is the most useful one quickly. And usually Google helps you because it puts the most clicked on the top, and the most clicked usually are the more reliable. Not always. So you have to gain your skills in evaluating the reliability and maybe the bias of a source of information, because a source of information may be reliable but biased. So, for instance, when you look for medical problems, medical entries, this is even more demanding than looking for climate, because you find everything. And even the most clicked websites in medical science may be wrong. And so even in climate, you have this problem. So try to make sure that you gain this ability. Browse the web quickly and get the reliable information. Don't take just the first one. Better if they are scientific papers. But even if they are scientific papers, look at the journal. What is the reputation of this journal? It's not difficult. You may think, how can get this ability? It's not difficult to get this ability. You just need to make experience in browsing the web. Try to browse the web, find information, and look at the information, look at how it looks, and of course get help from others who are more experienced. NASA is reliable, sometimes biased a little bit, but reliable. Okay, what is the Earth system? So first of all, we need to define what is a system. Okay, so let me just about the Earth as a system, background information. Just a system is defined as a group of interacting, interrelated, or interdependent parts that work together to form a whole. Okay, so what is then the Earth system? The Earth system is a group of interacting processes or interdependent parts that work together to form the, let's say, to form the evolution of the Earth and related processes as a whole. So the Earth system science, to give you an example, and it's not a coincidence that it's easier to find the definition of the Earth system science, includes atmospheric sciences, climate science, hydrology, volcanology, many others. Now, why it is complicated to find a definition of the Earth system? Because while it is quite clear what is the purpose, to describe how the Earth works, how the Earth evolves, to describe the dynamics of the Earth, you understand that when we say the Earth, nature, we may say also nature, we mean a set of several processes that are interacting each other. They are related. And we will see with more details, like climate, interacting with the water cycle, interacting with space sciences, because climate depends on the energy that is given by the sun. So it's important to study also the space sciences. It's also important because other planets have had a similar evolution with respect to the Earth. Understanding what happened to Mars, where we had water billions of years ago, and now there is nothing. We had an atmosphere in Mars, and now there is nothing. Understanding what happened in Mars enable us to understand what will happen in the future over the Earth. You know that the Earth system in the form we know it is not going to last forever. It will going to finish. Also the sun, it's not lasting forever. Of course, in the time span of the human life, not only ours, the human life, the life of the human species, probably the time span of the Earth, of the solar system life is much longer. So we are not concerned. Still, it's interesting from a philosophical point of view to accept that also the solar system, the Earth, life over the Earth is not going to last forever. So these processes are all related. So first we have to identify these processes, and we have two options. One option is to study them one by one. I study the water cycle. I study climate. And this is the traditional approach that it was followed in the past. Study these processes separately. Now, there is now we elaborated a more ambitious target. There is a movement that is called holistic. Holistic means to study a set of interrelated processes as a whole. So we have set a more ambitious target, which is to study the Earth system as a whole, which means that we have to describe the connection between the single part, the single processes. Difficult. So if I go back to my PowerPoint presentation, the Earth is a complex interrelated system. And here you can see some of the elements and sub-elements: water cycle, climate, atmospheric sciences, ecosystems, the carbon cycle, the human contribution. Now we realize that if we want to model the anthropogenic impact, we have to model the Earth system as a whole, and this whole should include the humans. It is not easy. It is not easy because it is already not easy to study the individual processes. So, for instance, the water cycle. You may think it's something that it's trivial. Actually, we understand only a minimal part of the water cycle. We still don't know what is the travel that a drop makes when it lands over the ground surface, and what is the path that this drop follows to get to the ocean. We don't know that. Some of the drops, of course, we know because you look at the river network, but before getting into the river, where does the drop go? Over the surface or in the underground? We don't know. We simply don't know. We are still debating whether floods are originated by old water or new water. Old water means that when you get precipitation, you get the flood, not for the effect of the water that you got at the time of the flooding or immediately before the flooding, you get the flood because the new water mobilizes old water. We still don't know this. We know, we determine that old water makes, in some context, a significant contribution, but still when we have to quantify, we don't know. So the water cycle is still unknown. And can you imagine the links between climate, water cycle? And this is important to know because I want to emphasize, I want to stress once again that we have not a full knowledge. We cannot make a perfect prediction. Okay, so the Earth system, as I said, the modern holistic view is treats the Earth system as a unified whole rather than the aggregation of separated parts. Okay. On the other hand, it's interesting to look at the components that have been studied in the past. And in the past, we used them to in the past, I mean 5 years ago, and not in 2 centuries ago, we used to represent the Earth system as an aggregation of domains called spheres. Spheres. And I think it is useful, at least for education, because this gives us the idea of what are the most important components, the most important processes. So the spheres that were traditionally considered are the atmosphere, the geosphere, the biosphere, and the hydrosphere. So the atmosphere, we know what is, and it's probably the sphere that we know better. The geosphere, it includes what we call also solid Earth. So includes the sciences, the processes that take place over the Earth and inside the Earth. The biosphere is the sphere of the living organisms, and the hydrosphere is the sphere of water, which is also part, the hydrosphere is part of the living organisms. So you can clearly see the connection. The geosphere is clearly related to the atmosphere. Think at volcanic eruptions, and they can modify climate. And then there are other spheres which are traditionally given lower priority. The cryosphere, snow and ice, the lithosphere, the land, so it's part of the geosphere, but it's only the land, the pedosphere, the soil, and the technosphere, humans. Humans are part of the technosphere. And it's interesting, but after the break, to look at the connection that we usually take into account, connections among each spheres and related ones. Questions before we make the break? Fifteen minutes break. Let me just close the micro and the video. Okay, time to restart. If somebody of you is a fan of mathematics and equations, don't be concerned because equations will come, okay? Because, you know, at the beginning, I prefer to be more narrative, but I am fully aware that we are in a school of engineering. It's true that not all of you are studying engineering, but we are in a school of engineering, so equations will come, okay? And maybe quite soon. Okay, so as I said, the Earth system traditionally was studied by individually focusing on a group of processes like water cycle, climate processes, and it is interesting, even within this reductionist view. The reductionist view is opposed to the holistic view. It is interesting to look at the connections among these spheres. The connections are understanding connections. It's a first step towards the elaboration of an holistic view. And therefore, what I would like to do now is to discuss with you these connections. And there are several possibilities. First of all, usually we limit our discussion to connections among selected spheres only, not all of them. But given that we focus on the connections among these spheres, which we focus on, it's interesting to look at the fluxes between them, fluxes of matter, okay? And there are several matters that are traveling along these spheres by following these connections. And the one first possibility, if we want to look at this exchange, fluxes of matters, one first possibility is to look at the carbon cycle. The carbon cycle, meaning that we look at carbon as the agent linking the spheres. And carbon, as you know, it's also relevant to climate, and in particular to climate change, because we believe that the increase of concentration of CO2 in the Earth system, in the atmosphere in particular, is one of the causes of climate change. And the carbon cycle describes these exchanges of carbon among the spheres from the atmosphere to the Earth, etc., etc. I think it is interesting to start with a short video, which I will play a little bit faster on YouTube. And to get the video, let me just go to the web page, which is okay, which is here. No, this is the PowerPoint. 1 second, because I got lost. Okay, give me 1 minute. The only thing is that I'm not sure. For the students remotely connected, I hope to be able to share the audio. Okay. Okay, first of all, there are some links to videos which I invite you to see, to watch. And we cannot, of course, we don't want to play all the videos in the class, because the class is to be devoted to discussions. I'm supposed to speak, not to show videos, but still there are some of them which I think are a nice introduction. And this is one first video on the carbon cycle from NOAA. And let me just see. Before starting it, it's on YouTube. So, okay, 1 second. Before starting it, I need to accelerate it a little bit, 1.5. It's short, it's 1 minute, but still I want to minimize the time. Let me see if the audio is there. I don't think so. 1 second. Okay, give me 1 second. I need. Okay, perfect. The audio is here. I think, I hope the students remotely connected can listen to it. Otherwise, you have the link. Let's move. Okay, let me just go back a second. In normal speed, here. For some reason, it doesn't move forward. I just wanted to focus on the part where it is explained the formation of the fossil fuels and the use of them. Just 1 second. Okay, let's forget about it. I think you already saw it, even if it was very accelerated. So carbon, it's and let me focus on here. Okay. The amount of carbon in the Earth system doesn't change. It's unchanged. First of all, let me say the Earth system is a closed system. It means that there are no fluxes of matter in and out. The only matter that is exchanged from the internal part of the Earth system to the external contour is energy. Otherwise, the Earth system is closed. Closed means, again, no fluxes of matter through the boundaries. The only matter that can go through the boundaries is energy. Energy from the sun and energy that from the Earth to the space. Otherwise, there is no flux of carbon in and out. Of course, there might be exceptions like meteorites. Okay, so it is possible that you get a mass entering into the Earth system from the space, but it is very occasional, like for asteroids, meteorites, etc. In normal conditions, it is closed, which means that the amount of water inside is the same. Unless you break the molecules of water into hydrogen and oxygen, the amount of water remains the same. So there is no waste, I mean, we cannot destroy water, okay? Or we can, but usually we don't do that. And the same for carbon, is the same amount. But carbon may be stored in sinks, like in the oceans, it may be stored in the underground in the form of fossil fuels. So what can be changed is the flux of carbon between the individual spheres. So carbon from the geosphere can go into the atmosphere if we burn fossil fuels, and can go from the atmosphere to the geosphere through the living organisms that once that they die, they get decomposed and can get buried into the geosphere in the form of fossil fuels, in the forms of oil. We know that oil has been formed maybe millions of years ago, and it's now stored in the underground. And when we extract the oil and burn it, we give back the carbon to the atmosphere. So we can change these fluxes, but the total amount of carbon is unchanged. And this figure shows to you what are these fluxes. Another important thing, which was shown in the video, is the role of the oceans. The oceans are carbon sinks, means that they can accumulate carbon, and they may release carbon. Typically with an increase of temperature, if there is an increase of temperature, the oceans release a huge amount of carbon potentially. And conversely, they can absorb carbon if they get colder. So the role of the ocean, the role of the geosphere to accumulate, to store carbon, it's important. And also the atmosphere can be a carbon, has a storage of carbon. And of course, if we in a way we perturbate the state of these carbon sinks, there are implications. There are implications in the processes. Vegetation absorbs carbon and gives from the atmosphere and gives it back to the geosphere. And you can see the different fluxes here, where the human component now it is considered to be very relevant. To quantify these fluxes, it's complicated and there is still uncertainty. We cannot estimate with certainty the amount of carbon that is released by human activity. Of course, you understand why, because we cannot really survey, we cannot really assess in detail any single release of carbon for human activity. And of course, we can get an understanding of the order of magnitude, but we cannot make a precise estimation. The scientific community is debating on that. So focusing on these exchanges of carbon is a way to understand the connection between spheres. So if we were able to focus on the exchange of carbon from the geosphere to the atmosphere, we would be able to understand the changes in climate. Changes in climate cause also a change in the ecosystems, which in turn may absorb carbon and give it back to the geosphere. It's an interesting way of looking at these connections. Another possible way is to look at the water cycle, which is connected to the carbon cycle. The water cycle, it is something that we know from the primary school, how it works. The water cycle describes the exchange of water between spheres. And the hydrological cycle or water cycle, you can use them as synonyms. Hydrology is the science of the water cycle. So we also use the term hydrological cycle to mean the water cycle. It is in essence very simple. As I said, we know it from the primary school, and apparently it is very simple. But actually, if we look at the details of the water cycle, it is not displayed here. Let me just go back to the web page. If we look at the details of the water cycle, it is much more complicated. And let me just open picture here, water cycle USGS. And let me see. So here there are several images. This is a classic one. This figure, which is public domain. 1 second. It is public domain, is very classic, and it is not high resolution here. Just 1 second. I need a, I think, 1 second. Okay, now it's high resolution, just 1 second. Anyway, I think, okay, good, here it is. Here you can see that a higher level of detail, it becomes a little bit more complicated because these fluxes, usually they are pictured in an aggregated way. So we say water from the atmosphere to the land. And then with this simplified view, we forget several subfluxes. So there might be water from the atmosphere to the land in the form of snow, in the form of rainfall, in the form of condensation, in the form of fog drip, for instance. And you understand, describing these individual processes, understanding these individual processes is not easy. Now, let me show you this other figure, which is a modern view of the water cycle. 1 second. And again, by the USGS, which shows clearly, you can see this is modern. Why? Because you clearly see here the human contribution. Grazing, water use, agricultural water use, reservoirs, and municipal water use, urban runoff, industrial water use, domestic water use. So now we gained the understanding that we need to include humans in the modeling of the water cycle and humans in the modeling of the carbon cycle. But indeed, when we want to describe mathematically these links, the complexity increases. And you understand that it's impossible to describe in detail what happens here. You need to simplify. Models are a simplified view of reality. And keep in mind that this is, all in all, a component of climate, because climate is driven by energy and is driven by exchanges of water, fluxes of water, which are powered by energy, and these exchanges of water drive climate. Climate is precipitation, is temperature. Temperature is related to water. So if it is difficult to describe the water cycle, you can understand this is only a part of climate. And describing climate is, of course, more complicated. You need simplified models. And you understand why there is uncertainty, why the predictions cannot be perfect, because the model is simplified. Okay, now, water cycle is another possibility. I look at the water cycle to describe these exchanges. Ideally, I should describe all of them together: carbon exchanges, water exchanges. Another possibility, energy exchanges. In terms of energy, the Earth system is not closed. I mean, the definition of a closed system doesn't exclude that you have exchanges of energy with through the boundaries. So, in particular, the Earth system receives the energy from the sun. It is the only source of energy. And then you have the suns that eats the ground through and stimulates several energy exchanges between the spheres. Let's try to look at some numbers, because I told you some numbers and the question will come. This is a quantification of energy exchanges between some selected spheres. So space, which is not a sphere, but it's the external part, it's the external domain where the Earth system is included. And then we have the atmosphere, we have the sea and land, etc. And let's suppose that we have 100 amount of energy coming from the sun. You see that 100 on the upper left corner. And you see a quantification, of course, it's a rough quantification of the split of this energy flux that comes from the sun. We have, if 100 comes from the sun, we have 19 absorbed by the atmosphere. We have 4 more or less absorbed by clouds. We have 23 reflected by clouds back into the space. And also we have a 7 reflected by the surface of the Earth. And then we get 47, which is absorbed by the surface. Now, let's look at the atmosphere. If we compare with the 100 that comes from the sun, keep in mind that the atmosphere receives individual contributions, contribution from the split that I just mentioned. So the 23 that is reflected by clouds comes into the atmosphere. The 19 that is absorbed by the atmosphere goes into the atmosphere. The 4 that is absorbed by clouds goes in the atmosphere, and the same for the 7 that is reflected by the surface. So if you look at the balance in the atmosphere, you have a 98 that from the atmosphere comes back to the land. So the land take 98 plus 47, and a 49 that goes back to the space. And a 9 that is emitted by clouds get into the space. These numbers may be not easy to interpret. Okay, if you want to get more details and you want to get convinced that every balance is broken even, so every balance is in equilibrium, let's go back to the original source of this figure. And the original source, you can find it here. Here there is the link. Let's copy it. Today the network is a bit lazy. Okay. Why the link doesn't work? Let me see. It looks fine. Jet stream atmosphere energy. Let me try again. No, it doesn't work. So let me just do this. Google. No. Energy balance. So let's see why the link is broken. Let me just jet stream atmosphere energy, and here is the jet stream atmosphere energy. Okay, probably we need to substitute here instead of weather.gov, NOAA.gov. Okay, I'll change it. Let's see here the balance. Plus 100 shortwave radiation from the sun, and you see here that the total budget is 100 incoming and 100 outgoing, with the split that I mentioned to you before. Atmosphere, so you have plus 19 absorbed shortwave radiation, minus 9 long wave radiation by clouds, and then you make any single component from this graph here. Okay, you make the sum of any single component, and you get at the end of the story plus 156 incoming and same number outgoing. And then the Earth's surface, you have 145 incoming because besides the sun, you get from the atmosphere, you get some energy, and minus 145 outgoing. So every balance here is broken even. Okay. It is interesting to look at these numbers, and don't be concerned. You don't need, you will not get questions on these individual numbers in any part of your exam, but it's important that you get a picture of these energy exchanges, sorry. Now, when we study these connections, we are particularly interested in the connections that can lead to a strong change. So we now recognize that, for instance, there might be small changes in climate that imply a big change in terms of flooding. And we are interested in this kind of amplifications. We are interested in the small perturbation that can originate a big change in processes which imply an hazard for us. We are interested in these dynamics of amplification, because these are the reasons why some hazards get humanity by surprise. Because we don't understand that, for instance, a small increase in rainfall, in extreme rainfall, in some situations can imply a very large increase of the risk of flood. And even if we have a kind of preliminary understanding of some of these situations, we still are not able to quantify them in a way to mitigate this risk of surprise. I want to give you an example. When you get, for instance, talking of a river, risk of flood, when you get a water level that is close to the level of the levee, of the protections against flooding, and you get the limit of flooding, you understand that you are in a situation that is safe. Until you don't have an overflow, you are safe. But as soon as there is an overflow over a levee, there is a collapse in a very short time of the levee itself. Unless the levee is equipped for allowing the overflowing, if you have a normal levee, let's say, which is not designed to resist to an overflow, once you get the overflow, it's a matter of seconds, and the levee gets destroyed. So you are still in a safe situation, but you understand that an increase of 1 centimeter of water level can cause a huge flooding. So for the Po River, for instance, sometimes it has been a matter of few centimeters of more river stage, and a big flood was originated. In 2000, when there was the flood in the Po River, it was the last one in 2000, the last big flood in the Po River. They, in some part of the levees, put the sandbags because to keep the water into the river. Sandbags means that you gain like 40 centimeters, half a meter of protection. And without the sandbags, we would have got a huge flood. So it was a matter of few centimeters, understand? So we have an understanding of some of these kind of thresholds, of this kind of amplification, but not all of them. And sometimes there are interactions also with the social system. If the social system has some of these kind of thresholds, which we don't understand very well. So we are interested in these kind of amplifications, as I said, which are called, in terms of system dynamics, leverage points. So points where you can have a leverage of certain variables, a sudden increase, an amplification. And from a mathematical point of view, you can call them, you can express them through non-linearities. When we say that a process is non-linear, we are much concerned. Why? Because we know that non-linearity can imply these amplifications, can imply these thresholds. So what is linearity then? And this is a basic definition that you need to know. What is linearity? Linearity means that you can apply the superposition principle. Look at the first equation. The first equation says that if you have a function of two variables that you sum, x plus y, it is the function of x plus y is equivalent to the function of x plus the function of y. It means that you apply, as I said, the superposition principle. The sum of the effect is given by the sum of the drivers. There is a second condition that we need to impose to ensure linearity, and this a multiplicative condition. A function of alpha times x is equal to alpha times the function of x. This means linearity. Linearity is not concerning. If you put in a graph this function x, depending on its independent variable, is a straight line. There is no sudden increase, no sharp increase. Okay. A straight line is something that is easily predictable. When I can apply the superposition principle, I can easily predict what happens. Let's think in terms of rainfall. Let's suppose that x and y are two rainfall depth. Okay, it means that I can obtain the risk of flooding of the sum of two rainfall by summing the two individual risks of the two depths. This is, of course, not true, because I just said that sometimes with flooding, a small increase can cause a huge increase of the damage, because a huge flood may occur. So it's clearly nonlinear. There is no superposition principle there. This is linearity. Non-linearity means that if you add to the function a small y, you have a result that is much larger. Okay. Okay, non-linearity means also that you may have tipping points, a terminology that in climate is extremely important. What is a tipping point? A tipping point is transition between two different equilibrium situations of a system, such that once it is overpassed and you get to another equilibrium situation, it is extremely difficult to go back. The Earth system is known to have several different equilibriums, state of equilibrium. Let's think about a forest. A forest is in equilibrium in a reasonable time frame, but if you cut the forest and then you get brushes over the land, the brushes don't allow the forest to grow back again. If we want to put back a forest, we have to intervene. We have to cut the brushes, put the trees there, and make sure that the brushes don't compete with the trees. So remove the brushes until the trees are, in a way, sufficiently grown up. But otherwise, the brushes will remain there forever. So you have this land that has two equilibrium situations, a forest and brushes. And once that you cut the forest and you go to the other equilibrium state, you can't go back spontaneously. Another example, which I think I already made to you, is the ice caps. The ice caps, we don't know if they tend to melt suddenly. It may happen because we know that there is a lot of water inside the ice caps, which is stored in internal lakes. And it may happen that, with the global warming and the reduction of the thickness of the ice, this water comes out suddenly. Suddenly means that the ice cap gets suddenly melted down, and you don't go back again because you don't have the low temperature to stimulate again the formation of ice. It's another equilibrium situation because we know that the Earth system has been for some time without ice caps, and for some time with the ice caps. We know that now we are in those, during one of those times where we have the ice caps. But the Earth system was in equilibrium even without the ice caps. So we could shift suddenly to the equilibrium situation without ice caps in a relatively short time, and we were not able to go back unless there is a decrease of solar energy and a decrease of the temperature, or there is or the human species disappears, and therefore the human emissions go suddenly to zero, and then maybe in some time, maybe in 200 years or in 1,000 years, we get a decrease of temperature and again the formation of the ice caps. These are tipping points. These are called tipping points and are a classical result of non-linearity. Non-linearity, okay? And it is extremely interesting to study these tipping points. And this is an example taken from Wikipedia of tipping elements. What are the tipping elements? The tipping elements are part of the system that can originate a tipping point. So, for instance, you see the ice caps there. Melt of Greenland ice sheet, the blue spot up there. And or Arctic sea ice loss, again, the blue spot on the right of the melt of Greenland. And then the Amazon forest. We are concerned by increased cutting of the Amazon forest that may cause the Amazon forest to disappear. The change in NASO amplitude or frequency. NASO is the variable through which we measure El Nino and La Nina. El Nino and La Nina are known to be extremely influential on climate. And typically, El Nino is caused by a change in temperature between the Western and the Eastern Pacific Ocean. So if you measure the temperature of the Pacific Ocean close to Australia and the temperature of the Pacific Ocean close to South America, and you compute the difference, this is an indicator of El Nino or La Nina. And when you have El Nino, you get more rainfall, I think, in the north of America, if I well remember. We will discuss El Nino. And when you get La Nina, you get a drought in Northern America. Okay. Maybe the opposite. I don't remember. I always make confusion between the two. But what is important here is the concept. So this difference in temperature causes movement of water, movement of cold and warm water in the Pacific Ocean. And depending on the temperature of the water that is brought from Australia to South America and vice versa, you get a change in climate. And we are concerned that this El Nino La Nina may cross a tipping point. Or the Gulf Stream. We know that the Gulf Stream is weakening. So there might be a sudden stop of the Gulf Stream, which means that the climate changes. Another example of a tipping point is the geomagnetic reversal, which we know has occurred in the past, which means that you have a sudden shift between the North and the South Pole in terms of the magnetic field. It happened in the past. It is an intensive field of research. People are trying to understand what could be the causes of a geomagnetic reversal, which wouldn't imply the disappearance of the human species, but would imply several consequences on the Earth system processes. So these tipping points are still poorly understood, and it's a matter of huge attention. And we have they are a big question mark, because think, for instance, of sea level rise. Sea level rise, I just said, it's not so relevant, the magnitude. It is 20 centimeters in 200 years, more or less. So it's not a big change. But what if the ice cap melts suddenly? And the sea level rise may increase suddenly meters, like 15 meters. And how can we predict this? So This is why some people, some scientists warn humanity. They say, what we can predict and what happened so far, it's still, I mean, I change the statement. What happened so far may be not an indication of what will happen into the future. We may cross tipping points. How can we predict them? Don't be concerned. There is a solution for an engineer, which is the introduction of safety factors or the use of worst cases. When you cannot predict, you can make a worst prediction and assume that the worst case will happen and see what is the effect. You may have no implications on your design project. And if you have no implication, there is no reason of concern. But this doesn't imply that in any case you have to avoid considering these tipping points. There are tipping points also in the human system, in the societal system. As I said, the societal system is more complicated today than in the past. And, you know, there are tipping points. Let's, for instance, the change of the university system, the Gelmini law of 2012 was a tipping point. And the change from engineering for many of the degree programs from a 5-year program to 3+2 was a tipping point. Of course, you can go back, but not so easy. Can you imagine going back? I don't think it is possible. And these are tipping points, but also in politics, there are some election outcomes that might be tipping points. And think of the past, some elections that marked really a tipping point. And it may be for the better. I'm not saying that it's a disaster. You don't have to assume that change is always negative. Change is essential. Change is essential to survive. Okay? Change is essential to survive. Think at nature. Nature is continuously changing because it wants to survive. You don't have to think that change is negative. Absolutely. Change is what we need. On the other hand, there are some implications of change that are negative, and we have to understand them. So in terms of politics, for instance, there have been tipping points that have been really positive. On the other hand, you understand that trying to predict them is a problem. On the other hand, you also know that the outcome from an election can be predicted statistically. When there is uncertainty, statistics helps you. It's essential. And a statistical prediction is as useful as a deterministic prediction. Deterministic means no uncertainty. I mean, if I have a prediction that gives to me an outcome with an uncertainty that is quantified, it's perfect. It's absolutely perfect. The problem of uncertainty is when you cannot quantify it. So statistics, it's indeed an helpful tool. And we will, unfortunately for you, because I know that statistics is not liked by students, we will focus on some statistics because it's essential in climate change. To deal with climate change and climate change adaptation and mitigation, it's essential to use statistics. And my target is, my dream, my ambition is to present to you statistics in a way that you like it. Let me see if I have, okay, let's stop here at Earth System Dynamics. Questions? Before you leave, let me just tell you one thing, 1 second. For Thursday, please make sure that from the PC from which you are attending the lecture, you have installed this software very quickly. Go on Google and just search for R project in this way with the slash. And if you look for R project, the first link is this package, which is free, open source. And there is download here. And then you select a mirror and select whatever you want. It's no problem. And depending on your platform, Linux, Mac, Windows, install it. In Windows is trivial. You have an installer, double click. Don't open it, just install it, okay? So we save some time. And when During the lecture, I will explain the process again, but if you install it during the lecture, you may lose some, some steps. If you can, please install it already now from the PC from which you are attending, so you can follow me by doing. You can learn by doing. Otherwise, learning a software by just looking at the screen becomes very boring. If you repeat what I'm doing, it's more exciting. Good. So again, you have to look in Google for this, our project. Thank you to the remote students. Bye.